we talk about moment bending moment diagram, and in general, this is basically column, right, and girder, and the composite beam, composite slab, and we assign the loading. So I'm gonna just quickly show you how quickly I can draw it. So assume we have, okay, once we open it, I'm gonna give you just another kind of kind of introduction about what you need to set it up. Once you choose the template and unit, you're gonna just go open, edit, and define the number of floors here, right? So I think I have only one floor, has a 12 feet tall. So this is just one example for this for framing exercise. And I define the grid. Go to grid here and open the grid. So you can define the x, y coordinate, x direction, y direction. So this is kind of grid you can define. Just if you just want to practice, do so. This is something easy. You can learn right away, right? Just do so tonight or tomorrow. Do because this is something you can just easily learn. Now, what we're gonna do is I'm gonna kind of redraw it just because I'm gonna walk through that quickly to composite beam design and procedure. So I'm gonna here, gonna click the quick draw. So I'm gonna drop the column. You see that? And then briefly I click, 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 click. So this is plan basis. If you click this, you drop the column below, right? I think Revit is pretty much the same, and the tool. So this is pretty easy to locate the column since we have grid. But some concrete project, usually they don't follow grid. So you may to draw some geometry in CAD and you import those reference line, and you may have to start draw that in a column using AutoCAD basis. So now, second, I'm gonna click the beams. I'm gonna draw the girder to tie the column. This time, I have a default here lateral column beam, lateral beam. It's part of auto selection beam, but I assume this is moment frame because this is 3D structure. So I need to at least have some lateral stability. So I'm gonna keep draw the girder. No. Undo. Yeah. So I drew that girder. I click this. So now since I have a nice grid system, you can use a quick draw like this, quick draw for secondary beam, right? Since we have a nice defined grid system here, quick draw, the property I'm gonna keep this auto selection composite beam. The pin means simply support connections. Number of beam, I'm gonna add a 2. Now I'm gonna add 2 beams in extraction. I choose it. If I hover, oh, that should be the other way around. Should be Y direction. No. Extraction. Yeah, extraction. Right. See that when you move this bay, it shows the dashed line. So I click this ESC key. Now I'm gonna refresh it. Yeah, this. Okay. So since I choose the pin connection, it show dot. It means it's simply supported connections. It's moment release. How do I know it? Right click. You see that end releases, right? And I and J for each node, the release and moment torsion and moment weak axis, strong axis. Basically, this beam is only just work for vertically. So moment 3 moment release is really the primary moment release pin. But since again this is 3D model, so somehow their setting is I think it's moment release in both directions, but basically you only need a moment 3, moment release. So I draw the beam. Now I'm gonna draw the metal deck, right? So let's see, since this is rectangular geometry, I click this. Since we already have, let me see, define section, deck section. So I already assigned 2 properties: 3-inch metal deck, 3.25-inch lightweight concrete, and 3-inch metal deck plus 4.5-inch normal weight concrete, right? Just I choose one normal weight concrete here. I'm gonna draw, click, and click drop. Now, since default is local x is 0, obviously it's parallel to x direction. So, but this is not right, right? Metal deck should be running perpendicular direction. So what do? You know what? Forget it. I'm gonna redraw it, right? There are many different ways. You need to. This is something. Yeah, try and error is gonna help you. So you have 2 choices. I know if you decide to draw it again, then you need to change the local axis 90. Click, hold down, and drop. So you rotate, right? Right? Rotate the orientation of metal deck. Or you can select this. You could go assign, and the shell decks here local axis. You could change the orientation angle 0 or 90. You could do that later. So here, I think it's geometry. I think we already drew it. Now time to assign the load. So since we define the section property, self-weight will be calculated automatically. Now we're gonna assign the design load, which for office space, I'm gonna assign. Before you do that, I'll show you what the load condition, load cases, load type, we have it. Dead load, superimposed dead load, and live load, and construction live load cases. I'm gonna select, assign the uniform area load, right? Dead load is basically self-weight, but superimposed dead load, I'm gonna assign 20. So I'm gonna assign 20 PSF, select again, and then live load, I'm gonna assign for now 100 PSF, right? And then select again, I'm gonna assign construction live load 20. But everything should be in the gravity direction. So I assigned all the load. Let's see here. So when you draw the column drop to the base, they automatically assign the boundary condition as a default pin. So you should be aware of it. And so right click the slab, see the properties right there, and the load is assigned there, right? So now here is quick and easy. So I'm gonna run the model, which you're gonna have a similar procedure. Most likely 99% is same as this. So your final presentation. So we run the analysis. Obviously, we check any bending moment diagram, right? So you should double check by hand. We practiced a few times homework 1 and homework 2, especially homework 2. Also last class, we double check this. No excuse. In the beginning, you should be able to get familiar with formula and punch it, because I've been receiving your homework. Somebody's understand, but you make a mistake. Even you write the same right number, but you mistake in calculation punching, right? You're gonna make a lot of mistake. Seriously, a lot of mistake. Yeah, it's natural. But you should be able to sense it. Oh, something wrong. Yeah, you should be able to double check one more time, triple time, by hand or confirm with software. Seriously, you should do that, right? Do not just bring this output, wrong output to the boss. Hey, here you go, Simon. Your boss is busier than you. You are supposed to bring the right answer. If you don't know how to do it, ask a question. But sometimes, like these hand calculations, right? They're not just punching. They're not just have enough time to double check for you. The important thing is the industry thing. You need time to get exercise, but obviously I want you to things that way so that you should kind of be more get the value from your boss. But anyway, so here assume that I double check, right? Every shift force diagram moment is right. Now, what do you need? You need to somehow, you're telling that, define that this is the composite beam module. You may have to define, okay, I'm going to use this beam. I'm going to just, two things. It's going to be simple. I select, this record model. Somehow they don't allow me to, okay. So this, okay. So I select this two beam is composite beam for this example. I assign go to design menu and override frame design procedure. I need to tell this is I'm running the composite beam design. So I just assign these two beams. I'm going to use a composite beam design. Next is setting up the load combination, right? It's simple. You're lucky, basically lucky. You don't have to do manually all this. All days I have to do it by manually. 100 load combination, sometimes I have to set it up manually. Now, if you set up load type, they give you for you. So I'm deleting this, right? I delete this. I just use the edit default design combination. I just choose composite beam design and bring all the load combination here. So ETAP's gonna set it up for you. This is kind of routine task, but you need to at least define your load pattern clearly. Dead load, superimposed dead load, live load, construction loads should be correctly also defined with also their type, right? So now I'm gonna run, right? Since I'm ready, I'm gonna run this design beam here. I'm just using default. I'm gonna run the design. So here I'm gonna put this on plan. Something is happened here. Oh, maybe right, 45 feet. Okay. So, oh, maybe because of vibration. I'll just ignore the vibration for study because it doesn't show much. So this one, so design composite beam, I need to explain later, but vibration I'm gonna turn off, none, because of vibration, it's give different big sizes. So I'm gonna redesign. So here, all right. So here, what you see? Let me just make this bigger. So last 1 minute, this final. So I run the composite beam design, right? So ETAPS kind of select the beams here, 21 by 44. I'm gonna click and select right click. Here is this today's final lesson. I explain all this. Composite beam works, right? Between concrete, metal deck slab, and steel, but it has to be tied with a shear stone, right? It has to be glued together because it's composite to get the composite action. With the composite action, this beam work like T-beam, much stronger and stiffer. We're gonna bring some simple model, we'll test it. Or if you have some model wood pieces, beam, glue together with the slab and beam, try to bend it. Or don't glue it, just leave it, you press down, see which one is stiffer. Right? It's physics or just phenomena. This is way it works. It's basically numerically we explain, right? With all kind of neutral axis and but here, ETAPS give this is from auto selection group. They recommend, okay, this is the beam is all workable. 21 by 44, right? Up to 27 by 84. What you need to get familiar with this is this today and until next week. You need to practice this. I explain more. right? I make a videotape more, I uploaded this more, but this is all workable sizes, right? The tabs highlighted lightest member, right? Lightest member, and also highlighted number of star, also number of camber, magnetic camber, stress ratio, right? Now let's look at it then. Strength check, you have to for safety. Serviceability check for deflection, right? Right? So this is to check backup calculation. So this member, right? See what we see based upon all the load combination. There is a factor load. This one is a pound foot. So it's a 220, yeah, 620 kfoot, right? So this is a moment, the design moment for permanent. Okay, go back to here. Construction bending moment. This one is again during the construction. Concrete is just pour, right? No composite action. That 1.2 depth plus 1.6 during the design construction phase is the maximum factor moment we can expect it. They check it, right, with our member bending capacity, which this is our W21 by 44 bending capacity, which most likely you can calculate it by 3.9 times Fy times G sub x, plastic section modulus. So that means this beam is fully braced, we assume, fully braced because of metal deck concrete. Even though wet, we assume the metal deck is temporarily fully braced, the beam. So this beam is fully braced, so then expected bending capacity is P times F sub y, right? In strength times Zx, section plastic section modulus. Understand section modulus, right? That is your nominal, your bending full plastic capacity of this section. It's simple. It's not just even island. Just I want you to at least understand this first one is during the construction phase, right? The only steel is contributed, but this steel beam should be strong enough to support this loading, which bending moment. Second one is obviously this factor moment, which is 1.2 depth, 1.2 depth, 1.6 live load, common condition with composite action. Their capacity we can have, if we have some 44 stud, we achieve some 73% of composite action, and our expecting bending capacity is this. But full bending means if we provide more stud, full the glue effect, so we can achieve some more higher bending capacity. So higher bend composite action means more bending strength and stiffening, but they are checking both. So this is strength check. Should be okay. Here is the stress ratio, right? Now deflection check is the same thing. I think first phase pre-composite, obviously deflection, steel beam deflection due to the weight of concrete. We should check it. Should be less than limits, right? And also post-composite deflection means deflections due to the superimposed download plus lateral deflection together. They check it. So this is expectation is 0.14 inches, but allowable is 0.18. Now this is good. So total camber, okay, in this case they recommend some camber. I think this is, I need to change to inches, but this is fit. But using camber, lateral deflection is they estimated it's allowed L over 316, right? The total deflection, since they propose a camber, total deflection minus camber is in anticipating the deflection should be less than L over 240. So L over 360 for live load, L over 240 for total dead load and live load. If you produce the camber, obviously you have to subtract back from your real deflection, total deflection, right? Because you assign camber. So this is a true. Here, last. Because of composite design, the member deflection calculation, you need to refer to using these calculations. So here, diagram, right? Beam deflection and report. Here, you should review it. You're gonna print out and include your part of final presentation and report. But again, just at least remember that you should, because it is composite design, you always have to use this output. Just here, you are looking at the design input, but this is the one I've been always see all the students they confuse or didn't listen carefully. You should not. Where is my diagram? Here, right? Use this live road here deflection case. Oh, here. This is finite analysis mode. You should not, must not use this live road, right, from deflection and use this deflection for your summary, because this is analysis mode. Right? ETABS doesn't know whether this is composite or independent slab and beam. So this is a finite element and 3D model. You just put the column, beam, and slab, right? Right? The beam and column is a frame element, right? Slab, we're using metal deck area element. But they, at this moment, they do not recognize whether they are glued together or not. So basically, this calculation, deflection, is basically based upon independent mode. Beam and slab is not connected, so they use, right, basic moment distribution, right? We calculate the, let's say, line load, equivalent line load for, let's say, live load, whatever the live load time, PSF, area load time, transmitter width, those line load they use, and they show the deflections diagram and numbers in this mode, which means they don't consider or they don't recognize any composite action here, right? Because of this only composite beam design, because the composite design is most like a beam design module, not analysis module. And frame modeling right here, they don't have any kind of input or such things. They ETABS recognize this slab and beam is tied together. This is more independent situation at this, but they know that they do the rotate down, but basically they do not understand composite action here. Only just composite beam design module here, right? When you submit the beam design, composite beam design, you should run composite beam here, right? Right? And then select, right click. So you should use this. So they show, oh, yeah, deflection here, right? And you could pull it out the calculation of the summary of here. So you need to use, you look at this calculation and confirm your beam design and deflection is acceptable or not. Because many students, even though I explained that, they always include live deflection check from here, which is wrong. You're gonna, if you're interested, do so. Your deflection in here, right here, with the composite action versus your deflection number here, substantially different. Because this analysis live deflection calculation doesn't consider composite action. So this deflection is much bigger than your composite beam deflection. Make sense? Right? 50% imputes, nothing. I think, yeah, at least this is something way the model set it up, it taps. I think because it is finite elements modeling, right? How can you define the slab and beam is connected? In this current the modeling, maybe if you're interested, we maybe do some mesh the slab, and mesh the beam. We maybe interior, maybe interconnect, we can just somehow officially, intentionally we connect and run it and see how they are close. When this just define mesh versus composite action beam design. So we can maybe test it. I'll show you maybe. Now maybe I can show you how much big still has a difference. But at least I want you to remember that we are interested in designing a beam, so you need to follow beam composite beam design, right? And then use this composite beam output to confirm. You're going to include this all design output, right? Beam size, and show this calculation, and let's follow along report and just look at this moment and see. I think you should be able to kind of double check this deflection here by hand too, similar to homework 2. But young modulus and you need to adjust it because this is composite beam. So what you need to adjust is young modulus, right? And moment of inertia. I think they may calculate here. Here, you show this based upon their composite action. Maybe okay, but I think you will talk about a little more. But I think this the video I'm gonna